Hi. Okay, so today I'd like to discuss about the regression estimation under the simple random sampling. Last time we talked about the ratio estimator, and at the end of it, we state that it is not always true that the ratio estimator is an unbiased estimator. Why is that? How can we find a better estimator? We emphasize that using the ratio estimator as well as the regression estimator, that we need to plot out the data that we are trying to estimate, which is the variable y, with the auxiliary information x, showing that x and y, they perform a linear relationship. Okay, so look back to this example. We have x and y plotted, and it shows that they, except for some of the outliers, then it shows a linear relationship for some of the points. They exhibit a linear relationship. So this is good to make use of the data x to help us to estimate the variable y. But this is not enough, because if we use ratio estimator, that means we also assume that the x and y line, the regression line, pass through the origin. The y-intercept equals to 0. Apparently, this example, the y-intercept doesn't seem to be equal to 0. So using ratio estimator may not be ideal. It could be biased. So we like to move on to regression estimation, that we do not simply have the regression line. We also assume that the y-intercept does have some implication in our regressions, in our estimation. So the line shows that the basic relationship between y and x. We try to fit a straight line passing through most of the line, the point of x and y. So the regression line are called the least square method, that we can obtain yi equals to alpha plus beta xi. In this case, alpha is the y-intercept, beta is the slope of our regression line. Therefore, for any given beta, that we can use our sample regression line, which is y bar minus beta x bar. This sample, this square line, could be an unbiased estimator for the population least square line, assuming they have the same slope, beta. By equating this two, then we can estimate this true population capital Y bar by y minus beta x bar plus beta capital X bar. So taking out the common factor, we have the unbiased estimator y bar equals to a sample y bar minus the slope beta multiplied to the difference between our sample x bar to the population x bar. And we have the indices LR to indicate this y bar estimator is obtained from the linear regressions. Okay, so in this case, this little y bar is an unbiased estimator for the capital Y bar. We can try to make use of this information to estimate the population mean. If we look at the nature of this estimator, if we look at the beta, which is the slope of the least square line, if the beta so happen to be equals to the ratio of y bar to x bar, then we multiply into this distance, canceling the x bar, and essentially we are achieving our ratio r times x bar from the population, so which is the same as the ratio estimator. When beta, or the slope, equals to 0, then the linear regression y bar would become the ordinary estimator because we don't have this bit. So the sample average y bar would be the unbiased estimator for the population y bar. We state that the estimator from linear regressions is an unbiased estimator for the population mean. We also want to look at the variance of our y bar under the linear regression line. So variance of y bar equals to variance of y bar minus beta x bar. Like how we did previously, that equals to the finite population correction factor multiplied to sigma square over n. Okay, so we take out the finite population correction factor, take out the n. The true variance of the population is equals to the variance using the least square line to approximate the variance of the populations. So this is similar to how we did it under the ratio estimator. Okay, so for a comparison, the only difference is the sigma, the variance from the population. Under the regression, we have beta instead of ratio to approximate the variance of the population. Again, if the population variance sigma is not given, then we can estimate the variance of our mean. So we will have a hat on top, then we will have a finite population correction factor for the estimated variance multiplied to s square. This s square is obtained from our sample using the linear regression estimation. Expanding that s square, that equals to sy square minus 2 beta sxy plus beta square sx square. Very similar to how we did under the ratio estimator, that we have the estimated variance from our sample, SR square, and the only difference is we have ratio, but we have a beta from our sample regression line. The question is, how do we define beta? How could we find the slope of our regression line in the sample? We said that the minimum variance that could be attained when beta is equals to sxy divided by sx square, that is the formula for the slope under the least square estimator. The optimum regression estimator could be expressed in the following. So now the y bar could be estimated by our sample y bar minus beta, whereas beta could equals to beta star, that is equals to sxy over sx square, multiplied to the difference between the sample x bar to the population x bar. When beta is equals to the slope of the least square line, that could be simplified as 1 minus rho square multiplied by sy square multiplied to the finite population correction factor divided by n, when rho is equals to the correlation between the variable x and y. I'm trying to prove this to you. Okay, so at optimal estimated variance, let's do that this way. Okay, at optimal, so it's again equals to the finite population correction factor multiplied to SL square divided by n. Expand this into the beta. Substitute beta equals to beta star at the optimal least square line slope. So substitute sxy over sx square into beta, and then we can have sxy square divided by sx square. Again, we have xxy square divided by sx squared. This is cancelled out. So what we have is still the finite population correction factor, and this is not the fact that we take this out. So that's become sy squared out of the bracket. Then this becomes 1 minus 2 rho square plus rho square, when rho equals to sxy divided by sx divided by sy. Okay. In other words, that would be expressed as 1 minus rho square multiplied to the finite population correction factor times sy squared divided by n. This bit looks so familiar. It is just the estimated variance under the ordinary estimation. Okay? Let's compare the regression estimator with the ordinary estimator to the regressions. Okay, under the ordinary estimation, y bar is obtained by taking the average of all of the y data. So the variance is equals to, or the estimated variance, should have a head on top. Estimated variance equals to finite population correction factor multiplied to sy squared over n. Regressions, we need to use our sample y bar minus beta times the difference between the x bar from the sample to the population to obtain our population y bar estimate. Then the variance, we just prove that equals to 1 minus rho square multiplied to sy squared divided by n times the finite population correction factor. So the only difference is 1 minus rho square. In this case, we can find that the variance at optimal, that is when beta, the slope of the regression line, equals to sxy divided by sx squared. Variance, or estimated variance, under the linear regression lines is always less than or equals to the variance obtained from the ordinary method. Why is that? Because of this factor 1 minus rho squared. So as long as rho does not equal to 0, or as long as we can find some relationship between x and y, the correlation does not equal to 0, this factor would be less than 1. So multiplying a less than 1 factor to the same value, we just find that variance of the least square estimator is always less than equals to the variance from the ordinary estimator, which is good news. So we need to find, the question is we need to find the variable x and y that they have some linear relationship and the correlation does not equal to 0. But however, even though they don't have any relationship, when rho equals to 0, there's no correlation between them. If that's equal to 0, then the factor is just 1. So variance of the least square mean is still as good as the ordinary estimator. So regression estimator is a very good estimator. Comparing the ratio and the regression. Okay, so under the ratio estimator, we find that the estimated variance equals to sy squared minus 2r sxy plus r squared sx squared times the common factor. So try to use the regression estimator, subtract to the linear regression estimator. So we know these, so sy squared will be gone. So the only thing left from this subtraction becomes r sx minus rho sx squared multiplied to the factor. So we have a square bracket, and this is always greater than 0. So this two, the product of these two is always greater equals to 0 again. So if a minus b is greater than 0, then a must be greater than b. So we can say that the linear regression estimator is always less than equal to the estimated variance of the regression estimator. So again, linear regression estimator is always as good as the or better than